materials in which the Coulomb interaction can be much larger than the bandwidth. And in that case, we don't necessarily we follow standard band theory. And we can get a whole host of phases of matter that are prohibited by standard band theory, including symmetry breaking phases, superconductivity, and even fractionalized phases. And but the standard setting for this kind of strong correlations really comes from strongly localized orbitals. And this, I think, makes some intuitive sense when electronic states are strongly localized around atomic sites. That means that they're less likely to tunnel from one site to another. And so the bandwidth becomes small in that very small tunneling amplitude. At the same time, when electrons are strongly localized at a lattice site, there's a very strong on-site Coulomb repulsion associated with the characteristic scale of how wide this orbital is. And so when you have tightly localized orbitals, it becomes more straightforward to get this kind of hierarchy where the Coulomb interaction can be larger than the bandwidth. And there's a pretty simple picture when you take localized orbitals and have very strong and have very little bandwidth, i.e. the Coulomb interaction is much larger than all the other scales in the problem, including temperature and the hopping. In that case, the charge is completely frozen at every lattice site, and if I have one electron per lattice site, I fill exactly one of these to avoid double occupancy and paying this energy U. So this is often called a Hubbard U interaction penalty. And this state describes what we call a Mott insulator, where the charge is completely frozen, despite the fact that if there weren't interactions, this state would be a metal. At the same time, the spins at each one of these lattice sites are totally free to thermally fluctuate, because there's nothing pinning these spins to be aligned with each other. At low temperature associated with having high order hopping processes, you can get antiferromagnetism with this. But to leading order, these spins are totally free, and these spins are called local moments for that reason, because they're localized at each lattice site and are free to fluctuate. But this state, I think, while it's pretty cool in some sense, you get spin charge separation and you get an insulator where you normally don't. It's a very classical state. There was no quantum mechanics really intrinsically involved in describing this. And that's because the interactions are totally classical. The only thing this Hubbard U says is we don't want double occupancy. And so in order to get really exciting quantum phases of matter, one needs to introduce the hopping and go to lower temperature. And at that point, you can describe things like high temperature superconductivity, strange metals, pseudogaps, all this stuff we associate with strong like correlated cuprate physics, for example, as well as heavy fermion systems. Now, all of this, I think, is in really sharp contrast to the other paradigmatic strongly correlated system, which is the quantum Hall effect. The quantum Hall effect is a very different setting. You take a two-dimensional electron gas at low density, and you add a very strong magnetic field. And when you add this strong magnetic field, you take the bottom of the band, which looks parabolic, and this parabolic band splits into Landau levels. So n equals 0, n equals 1, etc. And these Landau levels are topological bands. And I'll explain what that means in a variety of ways, but the simplest definition is that when you fill one of these topological bands, you get a quantized value of the Hall conductance of E squared over H. And that's what you see here when if you at this filling of 1 where you fill just the lowest Landau level, you get a Hall conductance of E squared over H. But then, and also it has totally homogeneous charge density, unlike localized orbitals where the charge density is strongly localized at every lattice site. And the Hamiltonian for describing electrons in these Landau levels when they're partially filled is really just the Coulomb interaction only. So density-density interactions for electrons inside this Landau level, and they have a characteristic scale of the Coulomb scale associated with the magnetic length, which is the size of these cyclotron orbits. But this simple form of the interaction, it looks simple here, it's just density-density interactions, but this betrays a lot of complexity inside here because all the states in these Landau levels are very delocalized. So the density-density interactions are no longer very classical anymore because all of the different orbitals inside these Landau levels overlap with each other a lot. And one way to understand why topology is associated with delocalization is actually through computing this commutator x with y. So x is the position operator for electrons in a Landau level, and y is the y position operator. And inside Landau levels, when these are projected to Landau levels, these actually don't commute anymore. And in general, for a topological band, the expectation value of this commutator is equal to the integral of the Berry curvature, which is what you integrate in order to get the topological invariant Chern number. So topological bands are actually characterized by having non-commuting position operators such that the average is equal, gives you the Chern number. And this is kind of like position and momentum uncertainty principle, except now it's position and position. So y acts like a momentum for x, and x acts like a momentum for y. If you want to localize things strongly in the x direction, you're forced to be totally delocalized along the y direction. So this delocalization leads you to you have to be a lot more creative in terms of how to minimize interaction energy. Previously, because electrons were localized, you could just avoid putting them on top of each other. Now they're delocalized, so you have to be a lot more creative and quantum about how you minimize the Coulomb energy. Another way in which delocalized states are enter in the physics quite strongly is that they give you strong ferromagnetism. And this is really like a many-body version of Hund's rule from chemistry. But one can understand it by just saying that if all the spins are aligned, the wave function has to be antisymmetric. And that means that two electrons can't be exactly on top of each other. So you get rid of the most short-range part of the Coulomb interaction. So it's using the Pauli uncertainty to favor this ferromagnetism. And this is probably the best understood ferromagnet theoretically, because it's such a clean problem, and yeah, the only term in the problem is this interaction. But something really remarkable happens when you fractionally fill this Landau level, and that's the fractional quantum Hall effect. And you can see here there are all these different fractions. Oh, sorry, where the Hall conductance becomes quantized and Rxx becomes zero. And that's indicative of a gapped state of matter. But the fact that this Hall conductance is fractional actually means that electrons have fractionalized. And the simplest way to understand this is really this amazing wave function that Laughlin wrote down back in 1983, which really describes the essence of why this happens in this system. So Laughlin took the fully filled state of the lowest Landau level, psi nu equals 1, where you occupy all the electrons here, and then attached this Jastrow factor, product I less than j, zi minus zj. And what this does is it makes electrons see other electrons as vortices. So when particle j wraps around particle I, the wave function's phase winds. Normally it would wind by 2 pi, just by the fact that there has to be a 0 by Pauli exclusion, and that comes from this initial factor, nu equals 1. But this additional factor causes it to wind by an additional 4 pi. So when you go all the way around, the full wave function winds by 6 pi. And that also, so each electron sees every other electron as 3 2 pi vortices. Furthermore, the amplitude of the wave function goes, the modulus squared of the wave function goes to 0 as zi minus ej to the 6th power. So there's a very deep 0 at the bottom at when two particles approach each other. And one can use this to actually argue that this is an exact ground state in the limit where interactions become parametrically short-ranged. So you can take a general interaction and expand it in powers of the range of the potential, and this becomes an exact ground state for a certain order in the expansion. So this can be used to really justify in this limit that the Laughlin wave function is exact. And then the Coulomb interaction is not perfectly short range. It has this long range tail, but it's been shown that when you adiabatically connect from these short range interactions to the Coulomb interactions, the state barely changes at all. It's like 99% overlap from Coulomb to the short range. So this seems to capture really the essential physics of of fractionalization in the lowest Landau level, at least for these Laughlin fractions. And also this vortex picture explains how this leads to fractional charge, because if each electron sees each other as three vortices, if I had a single vortex, if I'd done this three times, it would be like I added another electron to the system, but then removed it. So three of these would be a hole. But then if I only add one of these, that means it's a charge plus E over 3, which is a quasi-hole. So this construction both shows how electrons can avoid each other when their states are delocalized, and it also shows that in doing so, they fractionalize. Okay, and if there are any questions at any point during this, please interrupt me and let me know. Um, but okay. So now I'm going to move on to more forward-looking things. Um, there's really a huge space of possibilities beyond Landau levels for delocalized states. Landau levels are very special systems with totally homogeneous charge density and magnetic translation symmetry. And in general, in block bands, we have crystals and very inhomogeneous charge density, and none of the symmetries that typically characterize Landau levels. And this presents a lot of opportunities, but it also presents many challenges. So I'm going to emphasize this list of possibilities now. In general, when we have this kind of interacting density-density Hamiltonian, these density operators, you can think of them as scattering different momenta into other momenta. Like this density operator is like a delta function that's projected to the band, and that delta function scatters some plane wave with momentum k plus q into some plane wave with momentum k. And that's encapsulated here, where the scattering matrix element is lambda q of k, and it's related to the single particle wave functions in this manner, this overlap between psi k and psi k plus q. And this object really controls the interacting physics. It basically tells us how different Bloch states in the band respond to the Coulomb interaction. And when you're specifying the interacting physics of a Bloch band, you really have to just specify these matrix elements, and then that's enough to put it into your computer. And if you have an exact diagonalization code, figure out what the answer is for small system sizes. And just to really drive it home, like you can just like the only difference between modeling a system that has localized orbitals and the system that and the fractional quantum Hall effect is just a different choice of these lambda q of k's. And so really parameterizing the different kinds of strongly correlated systems we can realize we just need to understand the space of these and which phases different kinds of these have. Now, of course, this is a very, very huge space, but it makes the problem, I think, quite concrete. And now, because this is such an intimidating space, a lot of people have tried to specialize to basically these at small q, where there's a very geometric interpretation of them, which is often called quantum geometry. So in particular, the phase of these scatterings the gauge invariant part of the phase is determined by the Berry curvature. Expanding this at small q, you get 1 minus q dot a, where a is the Berry connection, and omega of k, the Berry curvature, which you integrate to get the topology of the band, is the curl of this k space vector potential. So this describes the gauge invariant phases of these scattering matrix elements at small q. But also the amplitude of these is important because it describes how strong the scattering actually is. And that's expanding that in small q, you get this symmetric tensor naturally shows up, and this is called the Fubini-Studi metric or quantum metric. And this is definitely a useful perspective to have, but I do want to emphasize before I go on that for the vast majority of interacting physics, the large Q part of these scatterings is very, very important. And there's no real reason to a priori specialize to small q, because, as I said before, and as is clear, especially in tightly localized systems, the short range part of the Coulomb interaction is very important, and oftentimes drives the biggest part of the energetics of the system. And short range in real space is all momentum space, including very large Q. So this can sometimes be useful, and I'm going to give an example soon about why the small q quantum geometry can actually tell us more than we might imagine. But in general, one needs to worry about these at all q. So that really brings this question, how can we really explore this list of possibilities and find the most exciting bands and most exciting bands to project interactions to and get strongly correlated physics? And can we put them in different categories and try to understand each category? And for this, I really want to emphasize how important Moiré materials has been for understanding, I think, this pretty broad theoretical question. But Moiré materials have given us a wide variety of systems in which electrons are strongly correlated because one can tune these materials in many different ways to realize narrow bands. But at the same time, the electrons in these materials tend to be very delocalized. Not always, but very, very often they tend to be very delocalized. And so they give us many examples of this type of problem that don't look like Landau levels, but don't look like Hubbard models either. And at the same and progress in experiments in these materials has also been very rapid. And so there's a lot of opportunity to get inspired by them, try to develop theories of their essential features, predict things for them, and iterate on a pretty fast timescale compared to materials where for every doping you need to make a whole new sample. For Moiré materials, you can make a sample and scan across the whole phase diagram just by changing the voltage in your device. So I want to emphasize that almost all of the progress I'm talking about in this talk really relies on amazing progress by experimental colleagues. And I'll touch on that as time goes on. But I'm really going to focus on two analytical limits that has come out of this interplay that, of course, and associated with strongly correlated topological bands that can be well beyond a standard Landau level. And the first is going to focus on electron fractionalization. So how to realize the fractional quantum Hall effect when you don't have a magnetic field. And in general, you have a block band whose wave functions may look pretty different than the wave functions from the Landau level. So for example, which wave functions lead to form factors that give us suitable interactions to realize these fractionalized states? And two, I'm going to talk about trying to bridge these two settings of strongly correlated physics. On the first slide, I talked about quote unquote Mott physics, where you have strongly localized orbitals and kind of classical interactions that then give way to physics of high temperature superconductivity and cuprates at lower temperatures. Can we see some of this physics in topological bands, and is there some twist that the topology gives us? And I'll give it a pretty tractable example of that later. Okay, so before I go into the rest of my talk, I'll pause for questions in case there are any. Okay, I'll go ahead. So I'm going to start with this fractional Chern insulator problem. So these fractional Chern insulators, as I said, they're characterized by hosting the fractional quantum Hall effect, and i.e. having electrons fractionalize and give a fractional Hall conductance, except in lattice Chern bands. So they form with a lattice and are intrinsically tied to the lattice, and and you're allowed to have a very small or zero magnetic field. In contrast to fractional quantum Hall systems, where the density of electrons is directly set by the magnetic field, here the density of electrons is not tied to the magnetic field in a way that I can specify how that's a sharp distinction later. Um, and these have really been sought after ever since 2011 because working at very, very high magnetic fields in experiment is pretty difficult and pretty expensive. These fractional quantum Hall effect is usually at 20 plus Tesla, and there aren't that many labs that have a 20 Tesla plus magnetic field. So making this also makes if you were able to realize these, you can make the physics of fractionalization much more accessible. And also because the energy scales and density scales aren't tied to the magnetic field anymore, in principle, you could get fractionalization at much higher temperatures because for fractional quantum Hall effect, you're really upper bounded by how strong the magnetic field is. Here, you're bounded. Fractional transinsulator, the natural energy scales are the atomic or crystalline energy scales associated with the system, which can be, in principle, much higher. And so these have really been strongly sought after for both theoretical and practical reasons. But a central question has been like which crystalline bands actually work. And there are two bits of conventional wisdom that I wanted to touch on that I think there's maybe a kernel of truth in each one, but at the same time, there are counterexamples to both. So one is that there's a flat topological band is enough. The main thing to worry about is having as small dispersion as possible. And once you have very little dispersion, um, if it's topological, you're probably good to go. And there's a kernel of truth in this, in that you really do want to have low dispersion. If you have a very dispersive band, you're going to have a metal. But also you want to have, but at the same time, only the lowest Landau level hosts this fractional quantum Hall effect, and maybe the first or second too, but the higher Landau levels don't. So almost all Landau levels don't give you the fractional quantum Hall effect. There's something special about the lowest few Landau levels that this point of view misses out on. The second point of view,
Question? Question?
yeah.
Yeah. What happens when the Landau level is high? What do we
Yeah, so
realize?
there's a pretty fun story about this that Michael Fogler has a really nice review on, but about correlated physics in high Landau levels. What turns out to happen is that basically electrons become very large in terms of very large cyclotron orbits, and the size of their orbit is much larger than the uncertainty in position associated with being in the band. So you can actually develop a semi-classical picture of them at when the Landau level index is sufficiently high. And then what you can show using that is that the ground state consists of basically a charge density wave of these very large orbitals because the interaction is essentially classical. But it's a very weird kind of charge density wave because the orbitals are so big. So it's not like a conventional charge density wave where you like localize things and keep them apart like that. The density of these states is almost completely homogeneous, but they do break translation symmetry in the same way as a charge density wave. But it's totally in contrast to the lower Landau levels where the orbitals are a lot smaller.
But in those charge density wave, are they simply charge density wave or are they charge density wave on top of integer quantum Hall effects?
Yeah, good question. So let's say I work at like I fill four Landau levels, and then in the fifth Landau level I make a charge density wave. Um, it'll have a integer quantum Hall effect associated with the four filled Landau levels. But the charge density wave in the fifth Landau level doesn't have any Hall conductance.
Oh, that's kind of surprising, isn't it?
Um, I think it's kind of similar to like a Wigner crystal at really low densities in the lowest Landau level that also doesn't contribute.
But the Wigler crystal may also have anions. It's not understood.
Yeah, so at like 1/7, for example, it could have anions. But I think the very, very low density, let's say like nu equals 1 over 20 something, then you can develop a semi-classical picture where it's just a totally simple Wigner crystal with no anions.
Is this fully understood?
Yeah. And that limit, where the interparticle separation is much bigger than the like magnetic length, there's no overlap between the wave functions. So you go back to a completely classical picture. It's like
Hmm.
large RS in the standard in Gellium, except with a magnetic field.
Mm. So just to make sure, for example, in your previous example, on the fifth Landau level, where some charge density wave develops, then I guess the original magnetic translation will be broken to some smaller magnetic translation.
Yeah, to associated with the periodicity of the crystal, it'll be discrete.
Yeah.
Yeah,
On top of this background, what is the new filling factor? Is it an integer or
it's integer. Yeah,
and it's an integer and there's no integer quantum Hall effect coming from this Landau level?
correct.
Uh-huh. I see.
Yeah,
Thanks.
yeah. Yeah, there are states where you can get crystals and have them contribute to the Hall conductance, but those are called Hall crystals, and they're a lot harder to realize. And I don't think they don't come from this kind of analysis. Um, okay, good. So yeah, so clearly there's something different between the lowest Landau level and these very high Landau levels, and that was noticed and really taken to a much deeper extent by Roy, where Roy in 2014 showed that if you mimic the lowest Landau level by having homogeneous Berry curvature and the homogeneous metric here, this metric condition is what differentiates the lowest Landau level from all the higher Landau levels. The higher Landau levels have a much larger value of this metric. If you mimic both of these, then in the special case of the lowest Landau level, you can show that you can fully mimic the interacting Hamiltonian entirely. And that really relies on really special analytic properties of the lowest Landau level specifically. In general, these quantum geometric features don't tell you everything about the wave functions, but there's a really beautiful property associated with the analytic structure that lets you make it work for the lowest Landau level and for certain related types of bands. Um, but at the same time, this is a very strong condition. You need to optimize both homogeneous Berry curvature and homogeneous Fubini-Study metric, and a generic block band will not give you this because if you were able to match this, you would also have totally homogeneous charge density in real space, and there are very few materials that have homogeneous charge density in real space. Um, but So what happened after 2014 is people looking for these states would try to write down tight binding models and optimize like 7 or 8 parameters to try to get as close as possible to this in order to and then try to truncate a bit and try to look for materials that looked close to this. But it was very difficult because you have to optimize so many things in order to get totally homogeneous Berry curvature and metric. Um, But we can actually do relax this very considerably. And we kind of came into this a bit serendipitously by studying this system called the system of twisted bilayer graphene, which is two layers of graphene twisted relative to each other. Um, and in particular, we studied this system in the so-called chiral limit, which is a analytically tractable limit that's a decent departure from the realistic limit, but I think offers a lot of insight. So in this chiral limit, what you do is you take one of the tunnelings in the system and you turn it off. So the in the system you have different areas of this moire lattice where the two lattices are twisted relative to each other. And so in this area, you have the A sublattice on top of the A sublattice. Here you have the A sublattice on top of the B sublattice. And in this chiral limit, you turn off the tunnelings at these AA points. And it's a pretty drastic approximation. It's made a little bit better by the fact that the system tends to have lattice relaxation in a way that really shrinks these AA sites and expands these AB sites. But it's still quite a drastic approximation. But nonetheless, we showed that when we studied twisted bilographene in this chiral limit, we were able to show that we can write down an exact Laughlin-like state. And remember, in the lowest Landau level, the way we conventionally understand why we get like a Lawson state, fractional state at 1/3 is by the fact that the state exists in the band. The state gives us an exact ground state for short range repulsion that in practice is connected to Coulomb and also gives us fractionalization. So the same type of argument we were able to develop in twisted bilayer graphene in this chiral limit. And I'll talk more about the physical insights associated with how, like, why this Laughlin state shows up in twisted bilayer graphene. But I want to give an idea of the context a bit first, which is what I'm doing here. And notably, uh, we noticed right away that we got this exact Laughlin state and we were able to make all these arguments, despite the fact that the Berry curvature was not homogeneous at all. It departed fairly strongly from this homogeneous lowest Landau level case. But there was a special condition which was satisfied, which was that the trace of this Fubini-Studi metric was equal to the Berry curvature at every point in the Brillouin zone. So even though these weren't equal to the lowest Landau level homogeneous values, the trace of this was equal to this everywhere, which is also satisfied by the lowest Landau level and not satisfied by any of the higher Landau levels. And it was over the next several years, this condition was developed, and in a couple slides, I'll give you the most updated physical understanding that we have about what this means. But it overall led to a revision in what we regard as quote unquote ideal quantum geometry. Previously, people were optimizing Berry curvature and this metric, but now we just need to worry about whether the trace of the metric is equal to the Berry curvature. And while this looks still pretty hard to satisfy because you need to make this work at every single momentum point, remarkably, this turns out to be a lot easier to satisfy than one thinks. So in this chiral limit, we just turned off one tunneling, which is think of tuning one parameter to 0. And then we tuned the twist angle to be the magic angle of the system. And that's the angle at which the bands become exactly flat in this chiral limit. So we turned off one parameter, which you can even think of as imposing a symmetry, and then we tuned one other parameter, and then we got this to be satisfied at every momentum point k. And this turns out to be actually quite generic. You don't need to tune many parameters in order to get this to be true. That'll become a bit more clear later. Anyway, this led to a revision into what we call ideal quantum geometry, and also made it much easier to satisfy and much easier to find moire materials that satisfy it. And there's a long list of them by now. And furthermore, it also led to the observation of fractional churn insulators in twisted bilayer graphene by Amir Jacobi's group a year later. So I want to talk through a bit about this experiment because it's a bit non-standard. They measured the inverse compressibility of the system, which basically lights up when a state is gapped. And for that, to understand that, we need to compare to this totally general formula called the strata formula for gapped states. It says that the charge per unit cell, nu, is equal to the Hall conductance times the flux per unit cell, magnetic flux, plus S. So for the ordinary fractional quantum Hall effect, you would drop the second term S, and then the filling would be equal to the would be equal to the Hall conductance times the flux, which is the standard thing where as you add more magnetic field, your filling increases by the Hall conductance. So the amount of electrons you have is proportional to the magnetic field. For fractional churn insulators, they're allowed to exist at 0 magnetic field. So they're allowed to have some density, even though this flux can be 0. And this S is a topological quantum number associated with how much it has in the 0 field limit, or you can think of it as how much bound charge the state has per unit cell. And this is just like the Hall conductance, this is another quantum number associated with the state. You can think of it as the quantum number associated with the symmetry enrichment by translation symmetry. So, and this differentiates fractional churn insulators from the standard fractional quantum Hall effect and is directly associated with the fact that fractional churn insulators are allowed to exist at 0 magnetic field. And the first fractional Chern insulator was, in the sense, was observed back in 2018, although at a very, very high magnetic field, because in this case, a very high magnetic field was needed in order to create the Chern bands that were then in a Hofstadter sense. So, in this sense, it was a fractional Chern insulator because there was charge bound to each lattice site. And in particular, this S is 1/3 for a standard fractional Chern insulator, associated with having one anion bound to every unit cell. In this case, Amir's group found that there was fractional Chern insulators at above around a 6 Tesla magnetic field. And this corresponded to this was allowed to be a lot smaller because this is in a system where there's a Chern insulator that goes all the way down to 0 magnetic field. And here, the magnetic field role is thought to be to improve the quality of the Chern bands. And we analyzed that soon after the experiment, and we were able to show that various indicators associated with how far you are away from the chiral limit that I mentioned on the previous slide, this field basically takes the TVG away from the chiral limit, and at least in this band geometry sense, brings it towards the values typical of the chiral limit. So this violation of this trace condition goes to 0 and drops off quite quickly. Also, there's an interaction-induced dispersion in the system that also drops off very quickly when you add a magnetic field. So it's hard to say super definitively, but we think that this is likely the role of the field in this experiment to improve the quality of the zero field Chern band to then stabilize these states. So
question. If
yeah.
we continue increasing the magnetic field, will the ideal condition be violated?
Eventually, when it actually systematically gets better and better, but the density of states in the band also shrinks. So like when you get to 2 pi magnetic field, flux quantum, the band essentially disappears. So it's a bit of a weird limit. Is in this straight formula, if you it's effectively a negative field. So when you have this Chern insulator here, the density of electrons in this Chern band is going down as the field is applied. So and eventually when you get to 2 pi flux, this Chern band becomes a Landau level relative to the insulator at 2 pi flux. So its density of states goes to 0. So it's a bit of a weird limit because it essentially turns into a Landau level on top of the 2 pi flux state.
I'm asking because if I look at the green curve, it goes to 0 with a non-zero slope still. So it appears if I extend the magnetic field to be even larger, this green curve will continue to go down.
I see. Yeah, I'm not sure I think these points are a little coarse because to get like more fractions here, you need to have a very large magnetic unit cell. So I'm not super confident that this is actually a harsh slope like this.
I
Uh,
see.
and I don't think we were very focused on getting this part precise. Um, but I think in any case, I don't think it's possible to continue beyond 1 here because the band that this describes kind of ceases to exist.
Okay.
Sorry, I have also a question. So about the bound charge, can you explain again what is its physical picture and why there is such a piece? And in particular, what parameters does it depend on?
Yeah, good question. So this bound charge is in a sense quantized. It has a fixed value for a fixed state of matter. So for the usual fractional quantum Hall effect, it's zero because the charge density is proportional to the flux. But for a fractional Chern insulator, you can kind of understand what it is from a zero field fractional Chern insulator. For a zero field fractional Chern insulator where I make a Laughlin state in this Chern band, the charge per unit cell will be a third at zero field, so this S will be one third, for example. And you can think of that as having one anion, one charge, one third particle for every unit cell in the system. But it's a topological quantum number in the same sense as Hall conductance is, and it's fixed for a given state of matter. And
I see. So it fully depends on the band structure and maybe the filling.
I would say it depends on the state of matter that the band structure and filling correspond to.
Okay,
So
so
you can continuously change the band structure, and as long as you don't close the gap, this S will remain the same.
I
Maybe
see.
put it in another way, this S is some data that characterizes the symmetry enriched topological phase.
Yeah.
Thanks.
Okay, great. Yeah, thank you for the questions. So I think with this context now, I want to move on to our kind of physical understanding of uh, what this condition does and why it leads to fractional Chern insulators and some outputs of that physical understanding. So wasn't until much later that we realized this, but this condition is actually, I think, a lot more intuitive in real space. So it turns out to be equivalent to this condition that I've boxed here that I'll now explain. So imagine you're interested in fractionally filling this red band over here. So you take some, and imagine this following thought experiment. You take some wave function from this band and you multiply it by z, which is x plus iy. So it's the complex coordinate in the plane. And you want to ask whether you stay within this band or whether you leave the band. If I completely stay within the band, then that corresponds to adding a zero of the wave function at r equals zero. So, and also around r equals zero, z psi will wind by 2 pi. So if you can multiply z psi by z and you fully stay within the band, so z psi equals pz psi, you can take a single particle wave function and add a vortex to it without leaving the band. And we want to do that because if you leave the band, then that costs kinetic energy. We're imagining we have a flat band here and we want to stay within this flat band and avoid exciting these high energy states. So, and if this condition turns out to be exactly equivalent to the quantum geometric condition I showed before. And because we can add vortices to any single particle state, we can also add these vortices for each particle to a many-body state, just by iterating this condition over and over again and applying it to each particle within the wave function. And so that lets us do things like take a fully filled wave function of this band and multiply by this product zi minus zj to the 2s. Then we can show that this full wave function is entirely within this band by just applying this condition over and over to each one of these particles and for each one of these factors. And the simplest case, so this lets us build fractional Chern insulators for a wide variety of bands. This condition does not require that the charge density or Berry curvature are uniform. You can have non-uniform density. You can also apply it to bands with any Chern number. So for example, like some Chern number 5 band. And it also works for multi-band systems as well. And there's some new physics in these that I think is still waiting to be understood. But today, so I really want to focus on just the simplest case because I think there's a lot of physics to understand here, which is just a single Chern number 1 band and in this case, we can really make a really direct comparison to a lowest Landau level in, I think, a quite physical way. So in particular, we can show that the wave functions of the band that satisfies this condition for term number one always factorize in the following way. So here I've written psi kl, which is the block state at momentum k. And for example, for twisted bilayer graphene, there's a layer index L. In another system, this could be some other orbital index independent of position. And then it splits into these two factors. One is fk of z times e to the minus k of r for some function k of r, times this other k independent part chi L of r. So this chi L of r part doesn't depend on which state of the band you're choosing because it doesn't have any momentum dependence. And we can identify this first part as a lowest Landau level in an inhomogeneous magnetic field. So for a homogeneous field, this k of r would be like z squared over 4, the standard Gaussian. But in an inhomogeneous field, you can have a more general function here. But the inhomogeneity of the field really doesn't affect any of the arguments. And then this chi L of r is a layer space spinner. And one can show actually that this chi L of r has a skyrmion texture in this layer space. So if I plot the Bloch sphere in layer space such that the north pole of the Bloch sphere, for example, is the top layer, the south pole is the bottom layer, and the equator are various equal weight superpositions, then if I plot the direction of the spinner for different positions r within the unit cell, it'll make a skyrmion texture like this with a non-trivial winding for every unit cell. And this leads to a pretty, I think, nice physical interpretation, which is that this wave function corresponds to electrons moving around in position space. They trace out some paths on this layer space Bloch sphere, and they pick up a Berry phase associated with moving on this Bloch sphere. And that Berry phase they pick up associated with the skyrmion texture exactly produces the magnetic field necessary for this lowest Landau level part.
I see. So the inhomogeneous magnetic field is determined by the skyrmion texture.
It's determined by the skyrmion texture as well as any additional phases in the Hamiltonian. But it has the same flux as the skyrmion texture.
Also, suppose there are not only two layers but more. How does this picture change?
Yeah, it's still skyrmion, but you can't see it as easily. So this is a skyrmion on S2. But if you had like 5 layers, it would be a skyrmion in complex CP4, so complex projective space. But all the CPNs have the same kind of skyrmions. They all have the right homotopy group.
Pi 2.
Yeah.
Mhm.
So this is just the one we can visualize, but if it had many layers, it would still give you the same kind of Berry phase. So yeah, that's a bit of a subtle point, but the exact inhomogeneous field here, the details of it can depend both on the profile of the spinner as well as any phases that are in the Hamiltonian that can also give you some, but some contributions here. But the point is that the Hamiltonian has no net flux, and the net flux associated with this field comes entirely from the skyrmion. So the exact profile can differ from this, but the flux comes from this.
Quick question.
Yeah.
So like for this kind of like visualization, does it mean that it only comes in when you apply even more magnetic field, like from the previous plot that you showed? So it has to come to that chiral limit that you mentioned.
So if you had this at zero magnetic field, which some systems basically do, like MOT2 is very close to satisfying this at zero magnetic field, then you should be good to go without adding any field. And sure enough, in MOT2 there's the fractional quantum anomalous Hall effect, which is a fractional translator at zero magnetic field. So this picture actually works very well for MOT2, even at zero field. Okay, great. And yeah, and then the other point is that because all the single particle states like this, any many-body state will factorize in this way, where there's a lowest Landau level part, many-body part, times this condensate-like form, product I chi Li over I, and this part in any matrix element will drop out entirely because these are normalized spinners. And so this lets you basically entirely map this zero field Chern band onto the problem of a lowest Landau level in this inhomogeneous field. So any theory you have for the lowest Landau level, you can apply to these bands. It's just you have to replace the external magnetic field with this internal field generated by the layer spinner. So that, for example, this lets you understand how to do flux attachment in zero field Chern bands, which I think is pretty unintuitive without this kind of picture.
I see. And to make this argument precise, one has to assume the red box.
Yes. Yeah.
Mhm.
Yeah. So to make this to get this exact factorization and this kind of exact parton fractionalization between this this part that feels flux and this fermionic part that feels flux and this boson part that generates the flux for it, this gives you this exact factorization and this exact parton type form. But you can maybe take the insights and adapt it even away from when this is perfectly satisfied by kind of treating this in a more like mean field type way, or like as an ansatz that's not exact. But yeah, this red box makes this totally rigorous. Okay, so now I think these fermions are nice for physical interpretation and they're nice for giving this mapping. But I want to talk about a situation in which they really come to life. Here they're kind of static and are just generating the flux for this lowest Landau level part. But in the next example, they'll really, I think they'll be the star of the show in a fun way.
Sorry, Patrick, before you continue, I really want to make a comment here. I
Oh
think
yeah.
the factorization form of the wave function is really beautiful.
Oh.
And the fact that pi2 of CPN is always Z, so that this result doesn't depend on how many layers we have. I'm very impressed by the beauty of this result.
Oh, okay. Thank you. Yeah, it was really fun to understand myself and like kind of come to it kind of serendipitously. Like I was just staring at these wave functions and noticing that they always split like this, and then eventually found that this could be interpreted as in an inhomogeneous field. But yeah, it took a while to fully build this picture and notice that it was a skyrmion and everything. So yeah, I'm happy that this description is satisfying.
Yeah.
So yeah, let me go on and talk about a situation where I think that it really comes to life even more. And this is based on recent experiments in rhombohedral graphene, where people have observed fractional translators, actually fractional quantum anomalous Hall effect at zero field. But I think the most interesting part of this is not the fractional translators. It's actually this Chern number 1 band at nu equals 1. And that's because, unlike all the previous examples, like MOT2 and twisted bilayer graphene, this Chern number 1 band is interaction generated. It is not there for in the standard band structure, and it's only there at nu equals 1, which corresponds to filling one out of the flavors of the band. So, for example, the state is spin polarized and valley polarized. There's no analogous state where you fill where you have nu equals 4, which would be the non-interacting band insulator corresponding to this. So this thing from experimental grounds, one can already argue that this has to be interaction generated. It can't be a band structure effect. And so it was a puzzle for a bit. Then many groups did Hartree-Fock type numerics and found that indeed, when you put Hartree-Fock onto the band structure, you originally don't have a gap. And even if you have this, there's believed to be a moire potential from this lower HBN layer. It's very far away from where these electrons are. But even if you crank this up, you don't get this Chern number 1 state. But when you add interactions, out pops a Chern number 1 state. And these 5 simultaneous papers all found this. But that immediately popped up a bunch of questions. Like, why is there a Chern number one state? What's the role of this Moiré potential? In particular, this system there were 5 layers of graphene in the system that they studied, and that corresponds to 5 pi Berry curvature, pi from each graphene's Dirac cone in one valley. And that 5 pi Berry curvature would naturally give you a Chern number 5 state if you opened up the typical gap, which was seen later actually in a different part of the phase diagram. But why Chern number 1? And all of these found it numerically, but I think it was a little unclear from a physical insight perspective. And so we wanted to kind of try to get the essential physics of this model and try to see if we could understand Chern number 1 in a kind of analytic and conceptual way. And the way we did that is we posited that we basically took an idealized limit of the system where it turns out at low density in the system, you can understand the block wave functions analytically from the fact that the two layers where the low energy degrees of freedom are the top layer and the bottom layer. And in the z direction, the system actually makes an SSH type model. So you can get the low energy block wave functions are related to the zero mode spinners of that SSH model. And we just took the approximation that these are exact across the entire band, and called this idealized limit of the system. And the crucial point is that these only depend on kx plus iky. They don't depend on k bar, and that actually makes it so that this condition, these wave functions satisfy this the vortexability condition I had on the previous slide. And on top of that, we also imposed short-range interactions, strong short-range interactions. But notably, we did not impose that the band has zero dispersion. This band has a lot of dispersion in it. There's a flat part of the band. I probably should have included a picture here. But there's a flat part of the band, but eventually it becomes very dispersive. And you have to include that dispersion to have a reasonable model of the system. But we added short-range interactions on top of that dispersion, and we assumed that these short-range interactions were rather strong. And what we found is that, again, the wave functions factorize, but in a bit of a more general way. So the many-body wave function psi Li of Ri, where Li are the layers, Ri are the particles, it turns out you can factor out a part that's exactly the lowest Landau level wave function at filling factor 1. And the reason for this is that for these short-range interactions, you need to add in zeros when particles approach each other. So when Zi approaches Zj, you need to have a zero. But that zero needs to continue from the top layer all the way down from all the layers. So because this is a multi-layer system, these contact interactions aren't naturally excluded by Pauli exclusion, because a particle on the top layer can be at the same position as the particle on the bottom layer, and that will pay Coulomb energy. And to guarantee that there are zeros all throughout the wave function, it turns out that the zeros need to be of the form Zi minus Zj. That lets you factor them out of the wave function and interpret it as a lowest Landau level wave function. Then the rest of the wave function is totally symmetric, this x, and it feels the opposite effective field as the first part of the wave function. So it feels a negative effective magnetic field. But because it feels an effective field and also has this layer degree of freedom, we can show that the single particle states associated with this boson wave function are layer-skyrmion states. So these bosons form layer-skyrmions throughout the system, and there's one layer-skyrmion for every boson for every electron. And there are many possibilities for these layer-skyrmion states. The skyrmions could form liquids, they could form lattices. There are many interesting possibilities. But the simplest one, which turns out to agree with Hartree-Fock to 99% accuracy, is these bosons form a vortex lattice state or skyrmion lattice. So this boson wave function has a condensate form, product I chi Li of Ri, such that then this wave function is exactly the same as the wave function I had here on the previous slide. So so that gives you a Chern number one ideal band. But notably, this wave function is now generated totally by interactions. In the previous example, that the Chern number one band was specified by the band structure of the material. Here, this Chern number one band comes from these short range interactions, and the form of this vortex lattice is not set in stone. It's chosen by minimizing the dispersion of the system, actually. And so because this skyrmion lattice is interaction generated, it's allowed to dynamically fluctuate. And there are collective modes associated with the fluctuations of the skyrmion lattice. And so we studied this assuming the simplest case corresponding to the Chern number one state. And we found the following spectrum. Down here, there are some phonon modes associated with the fact that this made a spontaneous lattice, and we didn't add a HBN moire, but if you add an HBN moire, it only affects these bottom states. I really want to focus on these top states here. So the state mz equals 2 corresponds to a state where the skyrmion in each unit cell deforms into an ellipse. And then this ellipse rotates chirally around its center. So it's a chiral skyrmion. You deform it into an ellipse, and that ellipse rotates chirally in one direction, associated with the fact that it only has +2 angular momentum and not -2. And similarly, there's an mz equals 3 state where you get this triangular deformation, and that also rotates chirally. And we found that we can write down analytical wave functions for all of these skyrmion shape modes, and it matches pretty much exactly with the time-dependent Hartree-Fock numerics for this state. Now, I should point out that all these results are kind of like these quantitative results are dependent on choosing this particular mean field type state. I think there's a good chance that at least these higher modes will survive beyond mean field for the following reason. One, this factorization into a lowest Landau level part times a layer-skyrmion part is totally general beyond mean field. And two, whether the skyrmions form a liquid or a solid is associated with the energetics associated with their center of mass. And that energy scale is a very small energy scale associated with this low energy phonon mode. This low energy phonon mode is associated with the shear movement of skyrmions, which changes their relative positions. In contrast, these higher modes are associated with the shape deformations, and they're at a much higher energy scale. So the precise form of the skyrmion wave function it seems like there are kind of two separate energy scales. One, this low energy scale, which determines the center of mass position of these skyrmions, whether they're a liquid or solid, and a much higher energy scale associated with the shape of the skyrmion. And so while we don't really know what's going on at this very low energy scale, they very well might not form a crystal. We believe that these higher modes associated with the shape will be there almost regardless of what state of matter they form. And these modes should be Raman active, so they should be detectable in experiment. And they're kind of similar in spirit to some modes in the fractional quantum Hall effect that people call chiral graviton modes because they also have mz equals 2 and rotate chirally. And those were recently discovered in Raman. So we anticipate that these could be resolved, and that would, in addition to being kind of cool, an experimental verification of these would also give us an idea of the different energy scales in this system, and help us answer other questions. Okay, so I think there are a lot of good questions, and I think I'm starting to go past the time limit. So I can maybe talk about a couple highlights in this section, or I can conclude either way.
Maybe go through some of the highlights very quickly.
Okay.
Thanks.
So in this section, I'm going to talk about a very different limit, trying to bridge the gap between Mott physics and topological bands. And to do that, I'm going to study a very simple case, which is half filling of a spin-full Chern band. And this will apply to twisted bilayer graphene as well. But in the interest of time, I'm not going to talk about the TBG specific stuff. So, but the central ingredient is concentrated charge density and Berry curvature. And the starting point is that most of the Berlin zone will look like a Hubbard band. So if you squint your eyes and don't see this red dot, then you'll think you're in a topologically trivial band and you think you're in a Hubbard model. But if you do look closer, you'll see that there's a small region here of width S, which is our small parameter, where all the Berry curvature is concentrated, all the non-trivial momentum dependence of the wave function is. And that this will encode the fact that all the Berry curvature is here, and that generates the topology. So when you fully fill this band, the Hall conductance will entirely come from the small region. Now, the conventional wisdom is that topological bands have delocalized states, and so therefore they have quantum Hall ferromagnetism. But instead, we find that there's a wide separation of scales between the charge energy scale and the spin energy scale, in which you have spin charge separation, as in Mott physics. So the charge is mostly frozen, but there are spin fluctuations at every site. But instead of localized states at every site, it turns out that these states are power law delocalized, but nonetheless, they don't overlap with each other very much. And that's really because any overlap in exchange energy is generated by this very small region, and the small region is parametrically small. And so the exchange energy scale is US squared, where S squared is the area of this region. So in this region, we can really make we can really make analytical comparisons and recover a lot of results in Mott physics, including, for example, the entropy in twisted bilayer graphene, despite the fact that the bands are topological. But I really want to focus here on transport in this system and K-resolved spectra, which really merge the Mott physics of the system with the fact that there's band topology. And this is solvable by roughly using the fact that interactions scatter electrons away from this band, scatter around the Berlin zone, and then scatter back, because interactions are non-local scatterings in momentum space. But all of these black arrows can be analytically solved for because they come from a very simple topologically trivial band. And it's these red arrows that encode the topology. And what we find is that instead of a typical Mott insulator, the Mott gap continuously closes at the gamma point when we just have interactions. When we add dispersion, we get a band opening in a very weird way. On this side, there's zero quasi-particle residue, which means that the excitations here are actually orthogonal to the electrons. So these are non-electron excitations, which we were puzzled by for a while. But then we were able to understand that exactly what these excitations are. And I think they're pretty fun. We called them trion excitations because in order to create them, you need to use this kind of operator. Details of this operator aren't super important. The main important thing for interpretation is that it has the same charge as the electron, same flavor as the electron, but it's dressed by this density operator. So it's an electron together with a density wave, basically. But it turns out to be perfectly orthogonal to the electron at gamma, and this orthogonality is actually topologically protected. So that's why there's zero quasi-particle residue here, because this excitation is created by this, but it can't be created by a single electron. And roughly that's because this thing is topologically trivial, but the electron has a 2-pi winding around this point. And I think one of the most fun things about it is that if you look at the 3 particles that make this thing up, all of them come from this heavy part of the band. They all come from this region here where the effective mass is very high. But this thing can be arbitrarily light. So you take 3 heavy things together, 3 heavy things, bring them together, and you get something that's arbitrarily light. And we also find that when we apply this to the superconducting normal state in twisted bilayer graphene, we get a Fermi surface of these things in the normal state. And so we think these will be important for understanding how pairing emerges in the system. Okay, yeah, let me conclude with my outlook slide and take questions.
Okay, thank you, Patrick, for the very interesting talk. Any other questions?
Sorry, I have a question. Can you go back to the page before the Mott physics? Yeah. This omega q is the dispersion relation. Is that
Yeah. Yeah. So
then?
yeah, these are the energies of the states.
Then it
Collective
seems
energy.
the system is in a gapless state because
Yeah.
at the gamma point it closes, right?
Yeah, so that's because the state is we assumed that we didn't have a Moiré potential here, so this describes a spontaneous crystal state of electrons. And so when you form a spontaneous crystal state of electrons, there are Goldstone modes associated with the fact that translation symmetry is spontaneously broken, i.e. phonon modes. And these are exactly those phonon modes.
Oh, okay, I see. So then when you talk about the topology, I mean C equals 1, it refers to the which band from this figure?
Oh, yeah, sorry. These are the collective modes of the band. So these aren't electron bands. These are like collective mode bands. So these bands are made out of an electron and a hole together.
Uh-huh. I see.
So I don't have the Hartree-Fock band structure corresponding to this ideal band plotted here.
Oh, okay, I see. Thanks.
Yeah.
Can you turn to the last page?
This one? Or-
Yeah. So is the Dirac trion essentially an electron dressed by two vortices?
Um, I don't know if I would say it's at least maybe there's a picture in which that's true. I don't it's a good question. I don't have the best I think I don't the I think what you're saying is maybe if you look microscopically in real space, it's an electron with two vortices nearby. But I think from the expression these trions essentially form totally on site at like basically the same AA site in the Moiré lattice. Um, and so it's the I don't think there's really a lot of spatial structure to them. They're like kind of their binding is like ultra local.
Oh,
Um, and and that's kind of seems a little unintuitive maybe because like why would they like how would that bind exactly on top of each other? But I think it's the way to understand it is really that um, these are the things that hybridize with electrons when you have local on-site interactions. The Hubbard interaction is a four fermion term that is totally on-site. And you can think of this four fermion term as taking one hole and turning it into a three particle object that's also totally on-site. And that's exactly this trion. And in fact, this trion actually appeared in Hubbard's original paper where he introduced his model. He actually solved the model using operators like this, but they haven't really been used too much in Hubbard physics from what I can tell, because they don't really come to life in the same way as they do here. Um, but the origin of how they form and why they're totally on site can be understood from just the original Hubbard model.
thanks.
Patrick, you said this Dirac trion has the same quantum numbers as the electron?
Yeah. Except for at the gamma point, it differs in terms of like crystalline symmetries. So it has different angular momentum at the gamma point, which is a consequence of the fact that it has different topology than the electron. So this trion forms a Chern number zero band, and the way to see that is that I can write it down in a smooth gauge for all momentum k, whereas the electron can't be in this band. And so, and that means that well, this has trivial angular momentum at every point. The electron has non-trivial angular momentum at the gamma point. So that's a symmetry way to see why they're orthogonal. But in general, they have to be orthogonal somewhere due to the topology.
But the topology refers to band topology.
Yes, refers to band topology.
Then if I add interaction that breaks the rotation symmetry so that angular momentum is not conserved, are they still orthogonal?
Yeah, there has to be some point in the Brillouin zone where where the single particle states created by acting on the vacuum with them. There has to be some point in the Brillouin zone where that overlap vanishes because that overlap has a 2 pi winding around the Brillouin zone.
Oh, I see. So am I understanding correctly that if I focus on this particular band structure and then add interaction, no matter how I add interaction, as long as I still preserve the translation symmetry, even if I break the rotation symmetry, then they are still orthogonal.
Yeah, yeah.
And
If
they're
you have
orthogonal.
translations, you can mess things up, but yeah, as long as you have translation.
So it seems this orthogonality is it may be possible to interpret this orthogonality as some UVR mixing, where the UV anomaly means that I have this particular type of band, and the IR property is this orthogonality somewhere in the Brillouin zone.
Yeah, I don't know if I would call it UV-IR mixing, but I would definitely say it's
I didn't say
yeah.
did I say UVR mixing? I mean UVR anomaly matching.
Oh yeah, yeah. I think I can see what you're saying, yeah. Yeah. Yeah, I think it's in the same spirit as anomaly matching in that way, yeah.
Mhm. Yeah, thank you.
Mhm.
Any further questions?
Sorry, just for this slide, this is like light bound of three heavy particles. This is, I thought you said it was charge density and electrons. They were shown.
Yeah, so the charge density is like a electron hole pair.
I see. Okay, okay.
Okay, if there's no more question, I have to represent everyone to thank Patrick again for the very interesting talk. Thank you, Patrick.
Thank you.
Yeah, bye.